Is this the place where we have finished?
Yes.
Yes? Okay, guys. So cameras are on. Come on, let's participate. So let's talk about the lymph nodes. So what's going to be happening here? So first of all, the lymph nodes, they are small lymphatic organs. Okay, so they are considered to be small lymphatic organs. They act as filters. They filter lymph. We already touched the part where we discussed what is lymph. And as you remember, lymph is just this excessive interstitial fluid that you get out of the connective tissue, because lymphatic vessels, they begin as the blind sacs within the connective tissue. The size is very important. It's very important that it is a range. It can be as small as 1 millimeter and as big as 2 centimeters. It's very important to know that the size is a range, because lymph node size changes all the time. So sometimes you're sick, so your lymph node gets bigger. You get better, the lymph nodes get smaller. So it just depends on the amount of things which is happening in your tissue. Lymph node has two vessels. It has the afferent lymphatic vessels and it has the efferent lymphatic vessels. You already remember that afferent lymphatic vessel is when lymphocytes go in, right? And efferent, they go out. When you talk about the lymph node, it's important to mention that they have lots of afferent. Okay, so lymph nodes, they have lots of afferent lymphatic vessels and no more than two efferent. And majority of the time, it's only one efferent. So even if there are two, even if they begin as two lymphatic vessels, they eventually fuse. So this is why it's very useful for us on the slide. If you see one lymphatic vessel at one place, right, it's definitely going to be efferent lymphatic vessel. Supporting elements are capsule, dense connective tissue. It sends deep protrusions. We call them trabecula. There's also reticular tissue, which is just loose connective tissue with the reticular fibers, reticular cells, and etc. Now, this is quite important as well. And in your slides, it's the older version. So you need to modify something here. So we have to discuss what's the pathway, right? So, okay, assuming I'm a lymphocyte within the afferent lymphatic vessel, right? I'm a lymphocyte within the afferent lymphatic. I'm coming in right now. I'm coming to the lymph node. What's the next thing, right? So what's the next thing I'm going to? What's the pathway? What's the route? So from the afferent lymphatic vessel, sorry. From the afferent lymphatic vessel, you're going to see that you reach the subcapsular sinus. So there's going to be a lymphatic vessel right under the capsule right here. This is the subcapsular sinus. So your lymphocytes within the afferent lymphatic vessel, they reach the subcapsular sinus. In your notes, it's written that after the subcapsular sinus, you go to trabecular sinus. So if you read your notes right now, it's written there trabecular sinus. It is like that in the book. In the book, that's what it says, that from the subcapsular sinus, you go to the trabecular. But last year, they changed it. In the, what's it called? In the lectures, they wrote something else. So from the subcapsular sinus, you go to the cortical sinus. Okay, so you're going to see that there's going to be cortical sinus. From the cortical sinus, you are going to go to the paracortical sinus. Paracortical sinus. From the paracortical sinus, you move to the medullary sinus, and from the medullary sinus, you go out through the efferent lymphatic vessel. So that's the lymphatic pathway. I repeat, you start with the afferent lymphatic vessel, subcapsular sinus, cortical, then paracortical, then medullary, then efferent. Do not forget that all of them are lymphatic vessels. and lymphatic vessels are generally more permeable than a blood vessel. So if, for example, I want to go out, I'm a lymphocyte, I reach the corticosinus, I want to leave the vessel. Can I do so? Absolutely. So lymphocyte, any lymphocyte, if it wants to, it can easily leave the corticosinus, stay within the lymph node, do its business, I don't know, proliferate, rest, whatever it wants to do. And then it has two options. It can either return to the lymph vessel and continue its pathway, right? So again, cortical, paracortical, medullary, efferent, or it can use a blood vessel. And you remember how do we call the blood vessels here? The ones that we use for movement?
HEV.
Very good. We call them high endothelial venules. Okay, so here we have the high endothelial venules. This is a blood vessel, specifically post-capillary venule, that instead of simple squamous endothelial cells, it has cuboidal endothelial cells. Basically, your lymphocytes has two options, right? So it's either they're using the lymphatic route or they're using the blood route. And you remember from last classes that 20% of lymphocytes use the lymphatic pathway and 80% use the blood pathway. Okay, before we talk about cells, let's go to the next slide and talk about general architecture of your lymph node. So lymph node is very similar to your thymus, okay? So it's quite similar in a way that it also has the outer cortex and the inner medulla. And you can see that the cortex is much darker because it also has more cells, and medulla is much lighter because it has less cells. So idea is pretty much the same, okay? So you see exactly the same situation here. Now, in the lymph node, the cortex is further subdivided into two. You have the outer cortex, okay? So you have the outer cortex, and you have the paracortex. Okay, so the outer cortex and the paracortex. And can you tell me what can you see within the outer cortex? What is here? What are those things?
Secondary nodules.
Very good. Those are the secondary lymphatic nodules, right? And you can see that the paler area in them, this is the germinal center. And the darkish line outside, this is going to be the mantle zone. So outer...
What is the second layer? There is the outer
mantle zone. Mantle zone. So
No.
germinal center is surrounded by the mantle zone.
Of the cortex. You said outer cortex?
Of the nodule. Lymph node, this is a lymph node, has two things.
Yeah.
The cortex has the outer cortex and the paracortex, which is the inner. So the outer cortex is just called outer cortex, that's it. So that's how you call it. So now that you know that within the outer cortex we have lots and lots of secondary lymphatic nodules, which lymphocyte will be dominant here?
B and
Very good, because don't forget that within the germinal center we have lots of B lymphocytes. They are proliferating, they are turning to become plasma cells, and etc. So this is why we say that outer cortex, right? So outer cortex is a B lymphocyte dependent zone. That's how you see it in the self-control test. B lymphocyte dependent area, B lymphocyte dependent zone. Right? So this is going to be the outer cortex. In the paracortex, the inner portion of the cortex of the lymph node, you see that there aren't secondary lymphatic nodules or follicles. There are some here, but they shouldn't be here. So it's a mistake. Maybe the tissue has kind of shifted. That's how it should look like. So what they look like here, they look like primary lymphatic nodules. So this is why the paracortex is a T lymphocyte dependent area, or T lymphocyte dependent zone. So this is quite important to know, that outer cortex B lymphocytes dominate here, paracortex T lymphocytes dominate here. Within the medulla, within the core of your lymph node, as you can see, we have the darker areas and we have the lighter areas, right? So there are some kind of dark islands of cells and we have some spaces between them. Your medulla, the medulla of the lymph node, generally consists of medullary sinuses and medullary cords. And if you took the embryo with me last semester, we kind of covered this, as I remember, that I think I told you this famous question by Professor Anton. He always asked this in embryo. What is the difference between cord and a tubule?
The space inside.
Yeah, lumen. Yeah,
Lumen.
so the tubule has a lumen. Like if you look at your, I don't know, aorta or any blood vessel, it is a tubule because it has a lumen. Esophagus, it is a tubule, it has a lumen. Trachea, it is a tubule, it has a lumen. Cords, like if you take a look at your charger right now, right? So my laptop charger, this is a cord. If I cut it, it's filled with something. There's some kind of wires inside. So it does not necessarily have a hollow space. It doesn't have a lumen. Or even if it has a lumen, its lumen is filled with something. It's already occupied with something. So what our medullary cords consist of, and this is very important to know. Medullary cords are going to consist of the B lymphocytes, plasma cells, dendritic cells, and macrophages. Okay, so B lymphocytes, plasma cells, dendritic cells, and macrophages. So if I were to ask this weird question, which one is actually a vessel? Is it the medullary cord or is it the medullary sinus?
The sinus.
The sinus, very good. So the sinus is going to be a vessel, like it will have a lumen, it will be, I don't know, able to transport a fluid of some sort. Cord is not, it's more of an island of cells. So we go back the slide, we talk about cells. So we know right now that our cortex is divided into two. We have the outer cortex, which is the B lymphocyte dominant area, and we have the paracortex. In the book it says inner, but you are not going to write paracortex. Paracortex is the T lymphocyte dominant. Medulla has cords and sinuses, we know this. So what are the cells that we need to discuss? Reticular cells, we know them from last semester. Those are the cells which make reticular fibers. Collagen type 3, it's pretty much straightforward. Macrophages, we also talked about the antigen presenting cell, professional antigen presenting cell, because it has MHC2 on its surface, MHC2 on its surface. So it's quite understandable. We have two cells now, two new cells, dendritic cells and follicular dendritic cells. And they are not the same thing. And they will test you on that you understand it, that they're not the same thing. Dendritic cell, we kind of saw it last class when we talked about professional antigen presenting cells, right? So dendritic cells is a third professional antigen presenting cell, together with the B lymphocyte and together with the macrophages. They are professional APCs because they do have MHC2 on their surface. Which kind of cell is it? It is a bone marrow derived, so very similar to your macrophage, okay? That it also has some kind of relations to the monocytes, okay? So monocyte also is related to the dendritic cell, but what is the major difference between dendritic cell and macrophage? Well, it is in the name. Dendritic cells, they have dendrites, they have lots and lots of food processes. You can think of the cell as the octopus, okay? That it has so many feed processes coming out, so it is reaching whatever it can. Macrophage, it's just one cell, okay? It doesn't have the food processes. So both of them are related to each other. Dendritic and macrophage cells, they are related. You could think about them as third cousins, okay? They're definitely related. They have the same common origin, but they look different. So hence we have to kind of differentiate them. You have said that dendritic cell is the antigen presenting cell, right? So in which area of the lymph node will it be?
Cortex.
Outer cortex.
Okay.
So in the outer cortex, we have here B lymphocytes. In the paracortex, we have T lymphocytes dominant. So where will be the dendritic cells if you had to choose, para or outer?
The outer.
Paracortex, because don't forget that those dendritic cells, they have MHC2 on their surface, so they need to be in the T cell rich area. And what is the T cell rich area? This is specifically the paracortex. Okay, so this is specifically the paracortex. There are some exceptions, but we'll talk about it. So for now, it's just the paracortex. Follicular dendritic cell, it's in the name, follicular dendritic cell. So where should it be? It should be in the follicle. What is a follicle? It is your secondary lymphatic nodule. That's what we call it. We call it lymphatic follicle. So inside of the germinal center, where the B lymphocytes are, you also have follicular dendritic cell. Okay, so where the germinal center is going to be, that's where the follicular dendritic cell is also going to be sitting. What is its job? It lacks MHC2. So could it be considered professional APC? Absolutely not. Okay, so it's, I don't know, other relative dendritic cell is definitely an APC. Follicular dendritic cell is not going to be an APC. But it is located in the germinal center of a lymphatic follicle. Then what is its job? You can think about follicular dendritic cell like without going details, because again, in immuno next year, you will learn all the details, everything you need to know, just generally, right? What is the job of the follicular dendritic cell? You can think about it as a cell which is a perv. It is a very perverted cell. It likes to watch things. And who does it like to watch? Specifically, your B lymphocytes. So as your B lymphocytes are proliferating in this germinal center, follicular dendritic cell is just sitting there with the popcorn, okay? Just watching your B lymphocytes proliferate. But follicular dendritic cell has a very important job. It has to make sure that your B lymphocytes do not proliferate too much, that there is a certain threshold, a certain allowed threshold of proliferation. What happens if your B lymphocyte proliferate too much? Your follicular dendritic cell goes to the mantle zone. It comes out from the germinal center and goes to the outer area. It goes to the mantle zone. And it tattles on the B lymphocyte to the T helper. It literally secretes a cytokine that makes sure that T helper is aware of this fact that B lymphocyte back there is proliferating a lot. And why would your T helper care? If B lymphocyte proliferates a lot, that means that whatever it is trying to kill is very dangerous. If it proliferates a lot, it means that it needs to use all of its power to kill whatever pathogen has come, right? It needs to make lots of plasma cells so they can make lots of antibodies, so you can definitely get rid of this dangerous pathogen. Agree with me, if this happens, you would want to remember this pathogen. You would definitely want to remember this. So if you see it next time, you don't waste time proliferating. So if this happens, if your B lymphocyte proliferates a lot, follicular dendritic cell tells about it to T helper. And T helper will make a cytokine. And this cytokine will go back to the B lymphocyte that is proliferating and force a couple of them to not become plasma cells, but to become memory cells. So follicular dendritic cells are very important in that manner because they decide, literally that's what happens, they decide if this pathogen is worth remembering or not, okay? So again, follicular dendritic cell is just watching, right? It's just kind of monitoring your B lymphocytes. If they proliferate too much, you're going to see that follicular dendritic cell is going to go to the T helper, which is sitting in the mantle zone, and T helper will make a cytokine that will force some, not all, some of the proliferating B lymphocytes to not become plasma cells. They will rather become memory cells. And what's going to happen to those memory cells? Well, they are going to go to the bone marrow. They're going to leave your lymph node, right? They're going to go to the bone marrow. They're going to use HEV to return to the bone marrow. And they're going to sit there. They're going to sit in the bone marrow and wait for their time, like those little tiny soldiers, okay, that remembered the war that was in, I don't know, God knows how long. Okay, I remember when that was there. So in case this pathogen again comes in, your memory cells get activated like this, and they're ready to, I don't know, secrete antibodies directly. So no need for proliferation. I can just directly make the antibody against that pathogen. That's very simplified version. Of course, there's lots and lots of cytokines involved, lots of processes. All of them will be learned next semester, next year, like 1 year from now in immuno. Okay, am I missing something? No. High endothelial value, okay. Lymph node, H and E. Outside is a capsule, obviously. This is the cortex. This is the medulla. You can see that some darker areas are here. Those are the medullary cords, right? So those are the medullary cords right here. The lighter areas are going to be medullary sinuses. Which kind of cells are within the medullary cords? B lymphocytes, plasma cells, macrophages, and dendritic cells. At the bottom here, you have a very lonely vessel. For 10 years now, they're saying that this is efferent lymphatic vessel. Why exactly? Nobody gives a solid reason. So I went around and I asked every one of them, and they seem to be agreeing on one fact, that it is alone. So this such a huge lymphatic vessel is just sitting alone. There's nothing like it. If you can take a look outside, right? There's nobody looking exactly like it. So it must be efferent lymphatic vessel. So that's the area of the efferent lymphatic vessel. Okay, so this is the outer cortex, correct? And which lymphocytes are dominant here? B, right? B lymphocyte, because there is the germinal centers here, and they're super active with the proliferating B lymphocytes. How about this area?
T lymphocytes.
Paracortex, and it is very dominant with T lymphocytes, yes. Now we magnify a little bit and you can see that under the capsule, there's this structure here. What could it be? And here they are as well.
Afferent.
Sinuses.
Afferent, let me answer that first. Afferent will be outside. They'll be outside of the capsule because they're entering the capsule, right? So, and for some reason we cannot see them. Like some professors say that those could be the branches of the afferent lymphatic vessels, branches of them, because they're above the capsule. But this particular sinus is beneath the capsule. And how do we call the sinus which is under the capsule? We call it subcapsular sinus, yes. So this is a subcapsular sinus, okay? Under here, this is a subcapsular sinus. Those ones, those are the subcapsular sinuses as well. You have said that this is the outer cortex and this is the paracortex, right? You can see some sinuses within the outer cortex. Those are going to be cortical sinuses. Like for example, this one, this could be considered as a cortical sinus. And then those little tiny vessels here, they are within the paracortex and they do not have blood inside of it, right? So no red blood cells are visible. So they could be paracortical sinuses. So those are going to be paracortical sinuses. From the capsule, you can see this thick structure. This is trabecular. Okay, so this is trabecular. It's very, very thick. This one as well. But then right next to it, you see very thin. This one, okay, those ones, those are going to be septa. So this is trabecular, this is septa. What's the major difference? The amount of connective tissue in it. So this is going to be trabecular, this is going to be the septa. Okay, efferent lymphatic vessel, subcapsular sinuses, medullary cords, medullary sinuses. Those are trabecular vessels. Like this is trabecular, a small artery, trabecular veins, and etc. Because you have to understand, somebody asked me this question that was very good. What's the purpose for trabecular? They could also ask you this, why do I have them here? Why are they here? Trabecular, they are an express road for the blood vessels. So for blood vessels which are outside, which is where the capsule, it's very difficult to get into the organ. They have to squeeze through the tissue in order to get inside. So the trabecular is like this highway that you just introduce, inside of which you have lots and lots of blood vessels. So trabecular allows you a much easier and deeper access to the organ. Access to who? Like to the blood vessels within the trabecular. It's much easier for them to be inside of the trabecular because they can go deeper and they can go faster. So more nutrients can be diffused, right? So much better for the organ in general. Okay, a question for you. What is this? Subcapsular sinus, right? This is going to be subcapsular sinus. What about this one?
Paracortical
sinus. Those are paracortical. Here they are. They're the paracortical because of the location. I point here and I tell you which other cell is present here except for the B lymphocyte. Which other cell is present here except for the B lymphocyte?
Follicular
dendritic cells.
Dendritic cell. Perfect. God, I love this group. Follicular dendritic cell. Okay, so follicular dendritic cell is going to be here. The same idea, I point here and I say which other cell is present here?
Dendritic cells.
Dendritic cell. So do I need to explain it? So you remember, follicular dendritic cells are within the germinal center. They're just curving their way through there. This is the paracortex here, which is dominant, is the T lymphocyte. Of course, dendritic cell is the antigen presenting cell, so it will be always near it. And last question here. T lymphocytes are only present in the paracortex. Correct or incorrect? T lymphocytes are only present in the paracortex.
False.
Because where else can they be?
Mental
zone. The mental zone.
Yes, mental zone. So here you could also have T lymphocytes. This is why if you actually open American histo book, you will see that they say outer cortex is B, T lymphocyte dependent zone. And paracortex is T lymphocyte only dependent zone. But in our university, in Hungary in general, they divide it. They say that outer cortex is B lymphocyte dominant. Here it is T lymphocyte dominant. In America, they definitely make sure that you know that T lymphocytes are also there. Okay,
Julia?
Medullary cords.
Julia, I have a question about the sinuses under the paracortex. What did we call them again? The paracortex sinus? Cortica?
Cortical, then paracortical. So, for example, if I go back, those are the cortical sinuses. They're within the outer cortex. And those are the paracortical sinuses because they're within the paracortex. In the book, if you open, you will not see them. In the book, they're called trabecular sinuses. Both of them in the book are called trabecular sinuses. But department disagrees.
Thank you.
Okay, so medullary cords, those are medullary sinuses. So those ones, the spaces. Okay, so it's not like this is a cord, between it is the sinus. No, specifically the white spaces. Okay, so the white transparent spaces, those are the medullary sinuses. This is a high endothelial venule. They use this picture for like the past 10 years. This is a very good picture and you can clearly see what's happening here. So how do I know that this is a high endothelial venule? I can see red blood cells inside. Okay, so those transparent red cells without the nuclei, they are red blood cells. And so it must be a blood vessel. It cannot be a lymphatic vessel because red blood cells are not present in the lymphatic vessels. And then you see that some cells which are lining the blood vessel, they are definitely not squamous, they are cuboidal. So the only option is that it is high endothelial venule, that it has endothelial cells which are tall, it has the blood vessels, and etc. some secondary lymphatic nodule right here, right? So you can see that germinal center, and this is the mantle zone. For you, spleen. Okay, let's talk about spleen. Size of a clenched fist, largest lymphatic organ, located in the upper left quadrant of the abdominal cavity, specifically where the 9th, 11th ribs are. So spleen is sitting between 9th and 11th ribs on the left. Very important to mention, week 14, you have anatomy ID practice exam, right? So you're gonna talk about just, you have like a list of structures which you have to just point and that's it. But sometimes when you pick the organ, like spleen or liver or lungs or heart, they ask you to put it into the anatomical position, because you know that your exam is downstairs, right? Where the downstairs rooms. And in the downstairs room, there is a skeleton that is just standing by the board. I'm not sure if you are in this room, if that's your classroom, but there is a skeleton just standing by the board. So what do? They hand you the organ and they say, go put it into the anatomical position in that skeleton. So that typically just like students lose their mind. They're like, what? So how can I do this? So it's very easy, just use your knowledge, right? So spleen is on the left side. You have to count the ribs. So you start from the 9th until the 11th rib. And it's very important that spleen is tilted. So when you hold it, you don't hold it just straight against the 9th, 11th rib. You tilt it a bit because they ask you, why are you tilting it? Because spleen is on the top of the stomach on the way. So stomach kind of pushes your spleen towards the periphery, so it has this tilted position. There is something which is called hilum. Hilum is the entrance and exit point of any organ. That's the area where blood vessels enter and leave. That's the area where arteries are going in and veins are coming out, okay? So that's called hilum. So hilum is also, it's not 90 degrees to your body. It's kind of, I don't know, 45 in a way, right? So hilum is going to be 45 to your horizontal plane. So yeah, okay. What's the function of the spleen? Morphological and immunological filter. Remember this because we'll be talking about it right now. So I'll be asking you. It has two areas. We call it white and red pulps. So when you cut your spleen, fresh spleen, not the one that you have in your anatomy practice, that has been marinated in the formalin for like minimum 3 years. No, like a fresh spleen in pathology, okay? So you take it out of the dead person and you cut it, you start slicing it. You see that the core of the spleen is red, okay? The core is red. And we call it a red pulp. So the consistency, like the actual core of the spleen is red, and we call it red pulp. And red pulp has morphological filtering function. Red pulp is morphological filter. But within that red pulp, you see white dots, like pimples, like zits, literally, like pimples, white dots. Those white dots are called white pulps. And white pulps, they have immunological filtering function. So remember this, that each pulp has a different function in a way. Spleen is surrounded by connective tissue capsule, the same idea, trabecular, blood vessels, etc. But the cell within the connective tissue capsule of the spleen is myofibroblast. This is very special. Like I can count how many organs have it. So spleen is one of them. So instead of myoepithelial cells, it actually has myofibroblasts. Okay, so it has myofibroblasts. So what does the cell do? It makes collagen fibers, and when it's needed, it can contract. So it will contract as well. Okay, so yeah, for what? Spleen is a very bloody organ because it constantly filters blood, so it always, at all times of the day or night, it will have lots and lots of blood in it. And sometimes you will need that blood. For example, if I'm eating, I'm digesting right now, all the blood should go to my GI. or suddenly I need to run, all of my blood needs to go to my skeletal muscles, right? So sometimes you might need that blood. So what happens is that literally the capsule will contract. So nerves will come to the capsule of the spleen, they will activate your myofibroblasts, and they will start to squeeze your spleen. They will literally squeeze whatever blood is present in the spleen. That's what is very fascinating about it. So through the myofibroblasts, the remnant blood, whatever blood is present in the spleen, could be taken out from it. It can be taken out from it. A question for you. Is spleen a vital organ? Vital means that you cannot live without it.
No.
No.
Absolutely not. So there are people who don't have spleen. You remove it for some reasons. For example, sickle cell anemia, right? So in African population, it's one of the disorders because of the genetical variations there. So in sickle cell anemia, you see that spleen gets enlarged. Why? Because all of those sickle red blood cells, they have a very weird shape. They get stuck in the spleen. The spleen cannot just get rid of them, right? So you will need to remove the spleen. So as we know, spleen has a filtering job. Specifically, it removes old red blood cells, bad red blood cells, malformed, the ones that were damaged. It also removes encapsulated bacteria. That's very important for you as a doctor. Spleen is the place where you remove encapsulated bacteria. So there are some bacteria that have a capsule around them. For example, I don't know, Neisseria meningitis, okay? So some kind of bacteria that could cause inflammation of your meninges, the coverings of the brain. It is encapsulated. So what you see is the following. If your patient does not have a spleen, he's more likely to be sick from encapsulated bacteria. So if you made the decision to remove the spleen of this patient for the rest of his life yearly needs to be vaccinated against encapsulated bacteria so he doesn't get sick as often. Okay, so because spleen is that place. Okay, we have said that it is a filter, but we definitely can live without it. Why? Because if you remove spleen, liver and kidney will adapt. They will take over the filtering job. They will start to remove old red blood cells or whatever additional things you have there. Okay, so they will take over that job.
But only spleen can destroy the encapsulated bacteria?
Correct. Only spleen can do that. So that's why even spleen, liver and kidney cannot do that. So only the macrophages of the spleen are capable of doing so. Yes. So that's why you will need to vaccinate your patient.
Julia, I have a question. Can we also say that spleen is a storage for blood? Can it store blood?
Yeah. You can, absolutely. Yes, absolutely. You can that. You can say that in a way it is a storage of blood, yes, because you know that, like, depending on your weight, you should have about 5 liters of blood, right, within your body. Depends on your weight. The more weight you have, the more blood you have. So does it mean that all of this blood is in my vessels? Of course not. It's distributed in some places, and one of those places is spleen. Okay, so sometimes you will see that as much as half a liter can be found in the spleen. So that's why it's such a good reservoir for blood, that if you need it, you can just squeeze it out and just put it into the vessels. So we talked about white pulp, we talked about red pulp. Please not forget that white pulp is immunological filter and red pulp is morphological filter. That's what I wanted. What does it mean, morphological filter? It means it is literally shaped like a filter. The way its structure is like a filter. It's literally shaped like a filter. So we will talk about it right now as well. So that's your spleen, that's the hilum, right? You can see some arteries going in, some veins coming out. Capsule, this is your white pulp, right? This is the white pulp. Everything else is red pulp. Everything else is red pulp. So this is the white pulp and this is the red pulp. You know, like, I'm not sure if you have this kind of, I don't know, weird fetish, weird urgency I really like to pump pimples, man. I love to do so. Like, you know, it really, I don't know, calms my nerves. So that's why when I first saw the spleen, when we first cut it, you know, the white pulp looks so juicy that when I took it, I just involuntarily started to pop it out like this. And I still remember the Professor Muller, he was like, "What are you doing?" I'm like, "I'm sorry, I just, you need to remove the spleen from me because I will be popping all of this white pulp out of it." So yeah, it does look like a zit. It does look like a pimple in the spleen. Okay, like a whitish, very nice thing that you want to pop. On the slide, of course, it doesn't look like it. It looks weird. So this is white pulp. How to draw it? We'll talk about it right now. So whenever you look at the white pulp, this is your white pulp. What does it look like?
Secondary lymph.
Nodule. Perfect. It looks like a secondary nodule. So how do I know? Is it a white pulp or is it secondary nodule? Always they ask this. Look for a blood vessel. White pulp will always have a blood vessel in it. Always. Secondary nodules do not have blood vessels in them. How do you call this blood vessel? You call it central arteriole. So if central arteriole is present, automatically this is your white pulp. If it is not present, automatically this is a secondary lymphatic nodule. The area outside of the central arteriole, so this blue, this is known as the pulse, periarterial lymphatic sheath. So this bluish area outside of the central arteriole, this is known as the pulse, periarterial lymphatic sheath. Which cell is dominant here? T lymphocyte. T lymphocytes are dominant within the pulse. So another thing which is worth mentioning, when you study, make sure that you kind of test yourself, that you compare. Let's do it now. What is the T lymphocyte dominant area in the lymphatic nodule?
The mantle zone.
The mantle zone.
Perfect. Perfect. Mantle zone. T lymphocyte dominant area in the lymphatic node.
Paracortex.
Amazing. Paracortex. T lymphocyte dominant area in the white pulp of the spleen.
Pulse.
The pulse.
Pulse. So make sure, it's very important for self-control tests and for the oral, when you study the lymphatic tissue, try to compare the organs, try to see where the lymphocytes are sitting, because it is such an easy question to ask. The T lymphocytes are sitting here in this organ, but they're sitting in another place in another organ. So make sure that you know this. Okay, so central arteriole, around it we have the pulse, the T lymphocyte dominant structures. Okay, right next to it you can see secondary lymphatic nodule. Okay, so right next to it you can see secondary lymphatic nodule. But this picture of the secondary lymphatic nodule is from third year immunology. So it's way too detailed, way modified. We're going to modify this picture. The two yellow colors go together. They go together. And this is your germinal center. Okay, so two yellow colors, they go together. This is your germinal center. As you can see, they're pointing out on this picture saying B cell corona, because next year in immuno, you will learn that B lymphocytes are not technically in the germinal center. They're technically between the germinal center and the mantle zone, which is called B cell corona. Okay, so again, this is way too much details for you. You don't need to know this. For you right now, right next to your central arteriole, surrounded by pulse, you can see here your germinal center with the B lymphocytes. Amazing. What is this white area outside? Well, not marginal. We call it mantle, right? So we call this as the mantle zone. This is known as the mantle zone. Outside this pinkish tissue, this is the perifollicular zone. Okay, perifollicular zone contains additional cells like macrophages, plasma cells, dendritic cells, I don't know, just some additional cells, reticular cells, just some additional cells which can be here. And then the border, this one, this is going to be your marginal zone. Okay, so for you, this is the marginal zone. For you, this is the marginal zone. Okay, just the border. Again, I'll show it on the slide. Yeah, I'll show you what's going on. Here, the secondary nodule, it has another name. it is known as the Malpighian corpuscle, but we don't call it Malpighian corpuscle anymore. Rarely they do, because there is a definite Malpighian corpuscle, and it is in the kidney. The renal corpuscle, it is Malpighian corpuscle, that's its our name. So glomerulus surrounded by the Bowman's capsule, its our name is Malpighian corpuscle. So that's why we don't use it here as often, because the one that we use it for is the kidney. Okay, so here's your white pulp. Again, your job is to always find a vessel. If you see central arteriole, it's definitely white pulp. If you don't see it, it is just secondary nodule. Again, now the red pulp. A red pulp of the spleen is very similar to medulla of a lymph node. So it consists of the same things, cords and sinuses, the same thing as we saw in the medulla of the lymph node. Here we call it cords of Billroth. The name is very important, cords of Billroth. And what do cords of Billroth consist of? Well, you can see a bunch of them here. Pretty much the same composition, like B lymphocytes, plasma cells, dendritic cells, macrophages, reticular cells, etc. But if you are an embryo or fetus, you see that within your red pulp cords, also megakaryocytes can be present. And as you know, megakaryocytes are precursors of platelets. So easily a question, why? Why are they here? Why megakaryocytes are in the cords of the spleen? That's your embryo 1 from last semester. You remember that we have hematopoietic organs in embryo. What is the first hematopoietic organ?
Yolk sac.
Yolk sac until the 2nd month. From 2nd month until 7th month, who?
Liver and spleen.
Liver. From 3rd until 6th month is the spleen. So the reason why megakaryocytes could be present in the cords of the red pulp is because spleen is a hematopoietic organ. So you will not only see megakaryocytes, you will also see proerythroblasts, you'll see, I don't know, promonocytes, any kind of cells which can give you any cell in the blood. Okay. So this is quite important slide as well, because we need to understand the red pulp. How does it work? Okay, we have splenic artery. It enters into trabecular, gives me trabecular artery. Trabecular artery enters into the white pulp as a central arteriole. As a central arteriole. Okay, so within your white pulp, you have central arteriole. How do you call this tissue around it?
Endothelium.
Pulse.
Pulse, very good. This is pulse. Which lymphocyte is dominant here?
T.
T lymphocyte, very good. Okay, here we have the T lymphocytes which are dominant. This is your secondary lymphatic nodule right next to it, right? So together, all of it is called white pulp. So your central arteriole has two possible scenarios, two possible ways of doing things. It either stays within the white pulp, and if your central arteriole stays within the white pulp, it gives you branches, and those branches are going to be supplying your marginal sinuses. Remember, there is a marginal zone, like a margin, like a border. There we'll have some blood vessels as well. They're called marginal sinuses. So they come from the central arteriole. Okay, so they're branches of central arteriole. Another scenario is that your central arteriole simply leaves the white pulp. So as it travels through the white pulp, it just goes out. And what does it enter? It enters the red pulp. Now the central arteriole is within the red pulp because all of it is the red pulp. As soon as your central arteriole leaves the white pulp, enters the red pulp, the name changes because you're central arteriole in the white pulp. Now you're in the red pulp. So what's your name? And this name gives me nightmares because I do not know how to pronounce it. Every professor says something else. I heard penicillar, penicular, okay, penicillar. I heard all of them, okay? So I do not know how to pronounce it. I do not know. So, and every time I forget to Google it. Every freaking time I forget to Google it. So that's why I'm just going to go with what Professor Anto used to say, and he says penicular. So I'm going to stick to it. Okay, so I don't know how to pronounce it. So penicular arteriole is central arteriole, but it is in the red pulp. So this is very important for you to remember. What is the blood vessel of a white pulp? Central arteriole. Yes. What is the blood vessel of the red pulp? Penicular, penicillar, penicillar, whatever. Okay, this vessel, penicular arteriole. Do not forget all of the outside things. This is your red pulp. And we have just covered that red pulp consists of cords and consists of sinuses, right? Two things are there. So your penicular arteriole, where will it empty? Into the cord or into the sinus?
To the sinus.
If you are a dog, yes. If you're an animal, if you're a cat, if you're a dog, that's what happens. Your penicular arteriole empties into the splenic sinus, and that's it. We call this circulation closed circulation. But don't forget, what is the job of the red pulp? It's morphological filter. It's shaped like a filter. So what is acting as the filter? Your cords of Billerov. They act as a net through which you kind of put your blood, right? So what happens? Your penicular arterioles, the blood in it, empties into the cords of Billerov. It passes, the blood passes through the cords of Billerov into the splenic sinuses. So we call this circulation as the open circulation, because for a short period of time, the blood, which was located within the penicular arterioles, right? So the blood which was here is actually not there anymore. It's passing through the filter. It's like the same as, I don't know, you guys have filters at your home, probably, like the one that you filter the water. When you put like a bucket of water, you first put it through a filter. So that filter is filled with things, with some kind of particles that filtrate your water. So the same idea is here, that the filter are the cords of Billerov, they are the filter. And the blood goes from the penicular arterioles to the splenic sinuses through those cords of Billerov. We call it open circulation. Okay, so because the blood leaves for a short period of time. It's not from a vessel to a vessel. It's not from penicular arteriole to the splenic sinus. It's not like this. This is closed circulation. Animals have closed circulation where blood is not being filtrated. We have a gap between the two vessels. Penicular arteriole, splenic sinus, they have a gap. And what is in this gap? You have the cords of Billerov are here, like a filter that is constantly filtrating your blood.
The gap is called the cord?
It's not really a gap, it's just a bunch of cells, like a cloth that is between the two vessels that you just use as a filter, right?
Okay.
Like a cloth. It's not really like a gap. This gap is filled with something. It's filled with those cords, right? With those cells that are actively filtrating your blood.
Okay.
Okay, you have said that central arteriole is surrounded by pulse. Yeah, and penicular arterioles are also going to be surrounded, but it's not called pulse, it's called PAM. So, and what does it stand for? Periarterial macrophage sheath. So central arterioles are surrounded by pulse, penicular arterioles are surrounded by pumps, by periarteriolar macrophage sheath. So like, for example, here, right? So sheathed capillaries, sorry, your penicular arterioles are sheathed. What is this? This is your pumps, okay? So this is your pumps. That's your macrophages. Tricky questions, APCs in the spleen. APCs are APCs everywhere, so it doesn't matter. So just because I say spleen or liver or something, the answer never changes. So it's still macrophages, dendritic cells, and B lymphocytes. So here is your spleen. It is less intensely washed out, so it is super bloody. Okay, the blood is still there, So as you can see, the red pulp is quite red for that reason, because it is filled with blood. Those are the white pulps. How can I prove to myself that those are the white pulps? I have to look for the blood vessels in them, right? So I have to look for the central arterioles in them. The tissue here, this is your capsule. This is your trabecular vein, some normal trabecular. So just lots and lots of trabeculars are here as well. Staining is H&E, right? Just less intensely washed out, just H&E. Okay, so look at the structure. This is a white pulp. How do you know that this is white pulp?
Presence of central
As a vessel. So here's your vessel. This is the vessel. How do you call this vessel?
central artery.
Central arteriole. How do you call the tissue right outside of it? Where is my red circle?
Pulse.
Pulse.
Okay, so pulse is not everything. It's just this area around the central arteriole. This is called pulse. And which lymphocytes are here?
T.
T lymphocytes,
T
right? So here
lymphocytes.
we'll have T lymphocytes, yes, so T cells. This is germinal center. Okay, this is germinal center. And this is the mantle zone, right? So germinal center, mantle zone. So this is your secondary lymphatic nodule right next to it. How do you call this tissue? This is the perifollicular zone, right? So this is the perifollicular zone. And very faint, which is not very sharp, it's very faint, barely visible, is going to be your marginal zone. Yes, this is the marginal zone right here. You have to know that we have two types of spleens. We have the less intensely washed out, so more bloody, and we have the more intensely washed out, so less bloody. What are they for? More intensely washed out is to see red pulp. The architecture of the white pulp here is lost. We do not see everything here. We don't, because you wash out more. So you lose the integrity, you lose the architecture. The less intensely washed out is to see white pulp specifically. So this slide is to focus on the white pulps. What do they have, right? So again, structure right next to it is also going to be white pulp. Central arteriole is right here. This is trabecular. Okay, so this is just connective tissue, which is nearby. So this is trabecular. This is the central arteriole. Tissue around it is going to be pulse, right? So this is pulse. Germinal center. All of this is going to be the mantle zone. So the outer area of the lymphatic nodule. This is the perifollicular zone, right? This is perifollicular zone. And right here, we will have the marginal zone. So this is known as the marginal zone. The area between them, this is going to be the red pulp, right? So the area between them, this is the red pulp. So again, you can see sinuses here, and between the sinuses, you can see cords of Billerov. So those whitish spaces, those are the sinuses, and between them are the cords of Billerov. Okay, you do it. What is this?
Capsule.
Capsule, very good. This?
Trabecular.
Trabecular, this is also trabecular. Okay, this?
White pulp.
White pulp. This?
The central arteriole.
Central arterial. This?
Pulse.
Pulse.
Germinal center.
Germinal center. Mental zone.
Mantle zone.
Perifollicular zone.
And
Marginal zone.
yes. So splenic sinus, right? The white things are the splenic sinuses, and those are going to be the cords of Billerov between them, right? So splenic sinuses, cords of Billerov. The same idea, splenic sinus, 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 the area between is going to be the cords of Billerov. This is the cords of Billerov. And you can kind of actually see that it's quite bloody. The cords of Billerov have lots and lots of red blood cells in it. So it's definitely less intensely washed out.
Only the white areas are called sinuses?
Yes, only the white areas are the sinuses. Everything else are the cords, yeah.
Mm-hmm.
Okay, more intensely washed out capsule, trabecular veins, trabecular artery is the major one here. Okay, so yeah. White pulp, but the integrity is lost. Like for example, I can see that this is the central arterial, maybe pulse around it. This is the secondary lymphatic nodule, but I cannot see the germinal center whatsoever. It's not there, right? So the integrity is definitely lost. Splenic sinus and narrow splenic sinus, cords of Billerov are between, right? Now take a look here. This is your white pulp, right? Everything else is the red pulp. And you can see that there is something within the red pulp, some kind of vessel. And this is a panicular arteriole. So this is the panicular arteriole. That's how it looks like. So the very similar looking to central arteriole. They look very much alike, but here it is sitting within the red pulp. The tissue outside of it, this is going to be pumps. And you see there's lots of nuclei around it, just lots of it just aggregating there. So this is going to be pumps. So this is the periarteriolar macrophage sheath, right? Just some sinuses and some cords. So again, sinuses, and cords are between. Again, very similar. So probably a branch of panicular arteriole, and you can see there are lots of cells around it. So this could be the pumps. Okay, so this could be the pumps. And again, same thing. So yeah, same thing. So white pulp could be panicular. Splenic sinuses, and cords of Billerov. Trabecular veins, trabecular arteries. Okay, 2 minutes break. Just gonna go to the bathroom and then we are going to continue with the skin. Last semester. Okay, so it's recording. Okay, so skin functions, blah, blah, blah. Read it at home. So what's another name for skin? It is also known as the integumentary system. So sometimes in self-control, you can see this. Integumentary system is your skin. What is it? It's an organ, and it is the largest organ there is. So skin is the organ, it is the largest organ there is. 3 layers, everybody knows: epidermis, dermis, hypodermis. Epidermis is keratinized epithelium. It is facing outside, so it has to be derived from ectoderm. Dermis is just a bunch of dense connective tissue responsible for support and strength. It has to come from the mesoderm because it is in the middle. Hypodermis is fat, adipose tissue, so it actually arises from mesenchyme, but mesenchyme comes from mesoderm. So in a way, hypodermis is also a part of mesoderm, just not directly, right? So at first, mesoderm first has to give rise to mesenchyme, and then it will become the fat. What are the derivatives of the epidermis? So that's your hair follicle, hair, sweat glands, sebaceous glands, nails, and mammary glands. You actually have a separate topic in your final oral, which literally says appendages of epidermis. No, appendages of skin. That's what it says. Appendages of skins, that's derivatives of epidermis. So you talk about this. And for the 50th time this semester, we have 2 different skins, thin and thick skin. You remember the difference. Layers, you know it. Basale, spinosum, granulosum, lucidum if you're in the thick skin, but this is a thin skin, so corneum. Basale has stem cells, spinosum has prickle cells, that's new, we'll talk about it, okay, so it has prickle cells. Granulosum has granules. Lucidum is not a separate layer, it is a sublayer of the corneum. Corneum contains dead cells. How do we call individual cell? We call it keratinocytes. So don't forget that keratinocytes in the stratum corneum are filled with keratin. Which kind of keratin is that? This is going to be soft keratin because we're talking about skin. In the nails and in the hair, this is going to be hard keratin. We'll also talk about the differences. How long are the keratinocytes stay dead within the stratum corneum? For 1 week. Okay, so when they reach this layer, they stay within the corneum for additional week. How long does it take them to reach this layer? Typically 2 to 3 weeks. Okay, so 2 to 3 weeks it takes keratinocyte to be born from the basale and finally reach the corneum. So your skin completely, your epidermis completely replaces itself every month. So next time I'm going to see you, you're going to be completely new people that I've never met in my life. Okay, that completely new skin, have no idea who you are, because this epidermis has been renewed several times already. Agree with me, it's very weird to keep a dead cell on the surface for a week and you stuff it with keratin as well, right? It's very weird. This kind of form of death, we call it terminal differentiation. Terminal differentiation means that you don't just remove the dead cell. No, you stuff it good with the keratin and you keep it there for additional week. That's like, I don't know, sadism, okay? It's very sadistic to keep a cell dead for additional week and filled with things. It's very sadistic. So this kind of form of cell death is called terminal differentiation. Okay, each layer a bit more details. Basale, you know everything, has tight junctions, desmosomes, new information. Additional cells are sitting here, such as melanocytes and Merkel cells. We'll talk about them today. So 2 additional cells are sitting in the basale. Spinosome, why do we call them? Because they have spines. Keratinocytes in this layer, they have spines. That's why we call them prickle cell. So prickle literally means that the cell is spinous. That if this is my one keratinocyte, this is another keratinocyte, those are the pricks, those are the spines. And what do we use those spines for? For connection. Okay, you're going to see that your keratinocytes will use the spines to attach to one another. So what can you see at the site of the spines? You can see desmosomes. So right where the prickles are, right where the spines are, that's where the desmosome could be. Sometimes this desmosome is way thicker than usual, so abnormally thick. So you call it as node of Bezos-Zero. Have you ever seen it? Never, ever. In my years of tutoring, I have never seen it, yet they always teach. So sometimes this desmosome is a bit too thick. We call it node of Bezos-Zero. Granulosome, very important piece of information, highly tested. Why do we call it granulosome? Because keratinocytes have here granules, okay? So if you take a look at them, this is the granulosome, right? Keratinocytes here, they have lots and lots of granules. How do we call those granules? We call them keratohyalin granules. Why are they important? Because they contain amino acids to make a protein. Which kind of protein? Filaggrin. Maybe you know this, maybe you don't, but all proteins consist of amino acids, right? Proteins are a sequence of amino acids. So within your keratohyalin granules, we have lots of amino acids, and those amino acids are needed to make filaggrin. And what's the purpose of filaggrin? What do we use it for? Let's go back to this picture. Stratum corneum has dead cells, and they are filled with keratin. And we call this keratin soft keratin because you're in the skin, right? But what is soft keratin? Soft keratin is a bunch, it's a lot, it's a bunch of keratin intermediate filaments. It's not one keratin intermediate filament, it's lots of them. So agree with me, I need to use something like a glue that will hold all of my keratin intermediate filaments together so they can be so sticky, so they can make your soft keratin, right? So what is this glue? The glue is filaggrin. Filaggrin is very important protein. It forces your keratin intermediate filaments to aggregate together, to concentrate, to stick to one another. As they stick to one another, you have the soft keratin. Because again, agree with me that every cell has keratin intermediate filament, right? Every cell has it because it is intermediate filament. But why not every cell has soft keratin? Why only skin has soft keratin? Because within its stratum granulosum, it has granules called keratohyalin granules. And those granules contain amino acids to make the glue that will hold everything together. And this glue is called filaggrin. You remember in the thymus, we also had keratin, you remember?
Yeah.
How did you call the structure that had the keratin?
Hazel's corpuscle.
Hassel's corpuscle. And Hassel's corpuscle was a bunch of type 6 epithelial reticular cells which were having keratin. So a question for you, why are they capable? How can they make keratin? What do they have?
Granules.
They have granules. Which kind of granules? Keratohyalin granules. What is within those granules?
Keratinocytes?
No. Keratinocyte has the granule.
Ah, okay.
So what is in the granule?
Keratin?
Keratin?
Mm-mm. Inside of it, you have amino acids. Inside of the granule, there are amino acids. What can I use these amino acids for?
To make
Filaggrin?
To make filaggrin. What's the use for filaggrin?
To stick the...
To hold them together?
To hold the keratin intermediate filaments together, to make the keratin that we're speaking. So do keratinocytes in the spinosum have soft keratin? No. They don't have it here. Why do they not have it there?
We don't have granules.
Because the granules are not in it. Without the granules, without the glue, you cannot do anything. So this is why soft keratin is only at the top layer. Is it clear?
Yeah.
Mm-hmm. Oh, thin skin versus...
They discharge the keratin?
They don't discharge it, they contain it. They stuff it within themselves. Because don't forget, they're dead here. They're dead. So how can they keep the shape? Only if keratin fills it up from the inside, right? And it's not just your keratin intermediate filaments. It's a bit different. It's a bunch of them glued together, which is called soft keratin, right? So it's not that you secrete it, you have it in you, inside.
Okay.
So everything here is understandable. We know all of it already, just additional thing. Eccrine sweat glands, apocrine sweat glands, sebaceous sweat glands. Which ones are present in the thick skin?
The eccrine sweat glands?
Mm-hmm. In the thick skin, you have the eccrine sweat glands only. Only the eccrine sweat glands. Why? Because the eccrine sweat glands are everywhere. You have them absolutely everywhere, thick and thin, doesn't matter. Okay, so they're everywhere. Apocrine sweat glands, as you remember from last semester, are limited locations. Where can we have them?
Axilla?
Armpit, which is axilla, nipples, periolar region, anus, pubic area, the weird places. Okay, so that's where you have the apocrine sweat glands. Sebaceous are associated with hair follicles. Does your thick skin have hair?
Thick, no.
No, could not possibly have the sebaceous. So if those three sweat glands are present in the thin skin, the thick skin only has the eccrine. Okay, I will describe this on the slide. Here we have our epidermis. This is the dermis, which is beneath. Dermis has two layers. The first layer is called papillary. The second is called reticular layer. Within the papillary layer, we have two collagens. We have collagen type 1 and collagen type 3. Another name for collagen type 3, it is also known as the reticular collagen. Take a look at the reticular layer. It has only collagen type 1. So not sure who was naming those things, but yeah, so reticular layer does not have reticular fibers. Okay, so I'm not sure why did they call it like that, but yeah, reticular layer does not have reticular fibers. It does not have collagen type 3. Papillary layer does. Okay, so papillary layer will have the reticular fibers. In addition, reticular layer also has coarse elastic fibers. So another weird thing. Coarse means rigid. Rigid is the opposite of elastic. So you have rigid elastic fibers. It's the same as saying healthy cancer. That's exactly the same way of saying, okay? So coarse elastic fibers. Yet it's very important that you say it. So apparently there are some kind of elastic fibers which are very rigid. They're not very stretchy. Another thing, papillary layer protrudes into the epidermis, and those protrusions are called dermal papilla. Okay, so those little tiny protrusions of the dermis into the epidermis, we call it dermal papilla. But you can see that your epidermis also protrudes backwards, right? You can see that it has a counteracting component to it. Those parts of the epidermis which are protruding back to the dermis, they are called epidermal ridges or rete ridges. Okay, so if I go here, how do you call this?
Dermal papilla.
Dermal papilla. How do you call this?
Epidermal ridges.
Epidermal ridges.
Rete ridge, right? This one?
Dermal.
Dermal
again,
papilla.
epidermal ridge again. Dermal papilla, epidermal ridge. So you can see that they're counteracting one another. For what? So you can get fat without stretch marks. Okay, so if you get fat suddenly, they cannot stretch as much, so you will actually have a scar very deep this way, which we call stria or stretch mark, right? So it cannot stretch, it cannot do that. We have super prominent, those structures, super prominent at your fingertip. Your fingerprints is very prominent dermal papillas like this, and epidermal ridges which are counteracting. They're so prominent that you can see them with the naked eye. Okay, those lines that you have on your palm, those are your dermal papillas protruding upwards. And the deepenings between them, those are the epidermal ridges which are going downwards. Okay, so they're super, super prominent. Okay, back to the collagen type 1 and coarse elastic fibers. The way they organize themselves in the reticular layer, we call it Langer's lines. So those Langer's lines, that's the way your collagen fibers and coarse elastic fibers run. Okay, that's the way they run in a certain region. If you want to be a plastic surgeon, you need to know those because you will never cut them. You'll never cut those lines like this, because if you cut it, you separate them. You separate the collagen 1 fibers. You cut it fully. It's now separated. So it will need much more time and much more energy to heal. And even if it heals, it won't heal nicely because you fully cut it, that's it. But if you cut along this line, right, along it, you do not cut it, you just cut along it. So the line is kept intact, you just cut right next to it. So the healing is amazing. So you have only thin line where the skin itself is, where the epidermis is, but not where the dermis. So that's why you actually take out appendix like this, right? So your scar for appendix is here. It's going to be like this. Even though it's much more useful to cut like this, but for aesthetic reasons, they cut it this way. They cut along the Langer's lines so you can heal better. Hypodermis, just fat, okay, nothing interesting. Very important is this, certain muscles will originate here. We call those muscles erector pili muscles. They start here and they are seen in the dermis. Okay, they originate in the hypodermis, but they're visible in the dermis. What is their job? They raise the hair follicle. So you have goosebumps. Okay, so goosebumps, this is the erector pili muscles working. When does it typically happen? When you're cold, excited, scared, okay, good music, you have the goosebumps, so it's also your erector pili muscles are reacting, they're raising your hair. Because you know, we're supposed to be mammals, and mammals have fur, so whenever we're in our not very resting state, our fur gets bigger, right? So our fur should get bigger. So the same thing is here. Huh. Okay. we know everything here. We know everything here. Let's talk about each cell individually. So here we have keratinocytes. Keratinocytes are dominant cells. Okay, they are dominant cells of the skin. We know everything about them, just we need to modify two things. So you remember keratin intermediate filaments, right? Keratin intermediate filaments. In keratinocytes, specifically, they have a name. They are called tonofilaments. So you know that every cell has those. Every cell has keratin intermediate filaments because it is intermediate filament. But if you're talking about keratinocytes specifically, its keratin intermediate filament is called tonofilament. Is it clear? And what do we do to tonofilaments? We stick them one to another by using filigrane, right? We stick them together so we can make soft keratin. How do we call soft keratin? We call it tonofibrils. So where is your tonofibril? It is in your stratum corneum because that's where the soft keratin is, right? So within your stratum corneum, that's where you have your tonofibrils. Where are your tonofilaments? They're within the stratum spinosum because it is just your keratin intermediate filament. Melanocytes, what's going on here? Melanocytes, dendritic cells, they have lots of projections like an octopus, neurocrest cell derived cell, makes melanin. Melanin is needed for protection of nucleus from ultraviolet light, right? So you need to protect your nucleus from UV, you use the melanin. When melanocytes make melanin, it puts it into an organelle. How do we call this organelle? We call it melanosome. Who needs to take those organelles? Your keratinocytes, okay? So keratinocytes which surround melanocytes, they need to suck up this melanosome. So how do they do so? They literally open their mouth. That's what keratinocytes do. They open their mouth, they engulf or phagocytose the tip of the melanocyte, and they do this. Okay, so they just suck up whatever melanosomes are present there. That's how they take it. How do you call this process? You call it pigment donation. Okay, so pigment donation, that's how you call it. Now, the amount of melanocytes. Every race has the same amount of melanocytes. Every race. Take a look at Icelandic person and, I don't know, African Nigerian person, which is right at the equator, right, where the sun shines so much. They have the same amount of melanocytes. What's the difference? The activity of melanocytes. Obviously, the more you're exposed to sun, the more active your melanocytes are going to be, the more melanin you will make, right? So don't forget about that. Do not forget that they also have no attachments to any cells. Melanocytes are just sitting in a stratum basale, but they have no connections to any other cell. Langerhans, antigen presenting cell. That's all you need to know. This is the APC of the skin specifically. Okay, so this is the macrophage of the skin. Langerhans cell is the macrophage of the skin. That's what it is. Okay, the same as the melanocyte, it does not have any connections to the neighboring keratinocyte. So the same. Merkel cell. This is the cell which is actually bound to keratinocytes. It has connections. It does, using the desmosomes attaches to them. What does it do? It is a nerve in a way. In a way, it is responsible for sensing things that happen into your skin. So it is a mechanoreceptor, like some kind of sensation, like a tactile feeling, right? So I do something to my skin, my Merkel cell will definitely feel it. As it gets stimulated by some kind of mechanical, I don't know, stimulus, your Merkel cell releases neurosecretory granules. And who will take all of those neurosecretory granules? A neuron, a nearby neuron. And those neurosecretory granules will fire up, will activate the action potential within this neuron. And the action potential starts traveling along other neurons until it reaches your brain and until you realize that you're definitely touching something or being touched. Okay, so Merkel cell is definitely some kind of mechanoreceptor. Speaking of mechanoreceptors, we have two types of them, generally, free nerve endings and encapsulated. Free nerve endings, they do not have a capsule. That's what it means. They do not have a capsule. Which kind of capsule? The Schwann cell and myelin sheath capsule. Have you heard about the cell before? Schwann cell? Right, so this is the cell that makes the myelin, and myelin is very important for propagation of action potential, right? So it travels faster and longer and etc. So free nerve endings do not have myelin sheath, they do not have Schwann cells, they're free of that capsule. So they're very important for touch, heat, and cold. Encapsulated do have a capsule around them. They do have the myelin sheath with the Schwann cells. So this is going to be your Pacinian, Meissner's, and Ruffini's corpuscles. Those are the three types of the encapsulated nerves. So the first one is Pacinian, always comes up because it's so weirdly beautiful. It's like, I don't know, a doodle that you draw sometimes. Okay, so that's where it is. It's very deep. It's located very deep. It's somewhere in a deeper dermis, also almost your hypodermis. It is sensing pressure and vibration. So that's why in order to activate it, you need to press deep, right? So you need to sense very, very deep with your fingertips. You need to press deep, and that's when the Pacinian corpuscle gets activated. Or vibration, right? So just the waves are traveling way deeper. So this is how the Pacinian corpuscle looks like. This is your nerve. Okay, this is the nerve, and this is the capsule that is outside of it. This is the capsule which is outside of it. What are those nuclei? Those are Schwann cells. Okay, those are the Schwann cells right here. What about this? This is your myelin sheath. So obviously next semester neurohistology will talk way more about it, but that's for now. Okay, those little tiny nuclei, those are going to be your Schwann cells. And this structure right here, this is going to be your myelin sheath. Okay, so this is the myelin sheath. Very important, what's its job? Pressure and vibration. Meissner's corpuscle. So here we have inside of the dermal papilla, inside of the protrusion of the papillary dermis into the epidermis, right? Where do we typically have it? In the hairless skin. So it is your thick skin and lips. Okay, that's the place where the Meissner's corpuscles are located. And because they're so superficially located, what is their job? They're very sensitive to light touch. And you can do experiment yourself. Just barely touch your palmar surface with your finger. Okay, it tickles, it's very tingling sensation because that's your Meissner's corpuscles going ballistic right now because you're barely touching them. Okay, so that's your Meissner's corpuscles right here. Ruffini's corpuscle, the most primitive of them all, the most primitive. Sitting in the reticular layer of the dermis. Okay, so that's where that's where Ruffini's is sitting. It is a neuron, the most simplest encapsulated mechanoreceptor, and through it, collagen fibers are passing. So through the Ruffini's, collagen fibers are passing through it. Why is it the most simplest? Because anything you do to your skin, anything, touch it, I don't know, you displace those collagens, you displace them. And as you displace them, who is aware of that? Your Ruffini's. It's very similar to analogy, like, you know, I'm not sure if you have ever seen like old vintage shops. When you open the door, the bell starts ringing, right? So it's like the security system there. When you open the door, the bell starts ringing. The same idea is here. You do anything, the collagen fiber gets displaced. And where is this collagen fiber? It is kind of traversing through your Ruffini's. So Ruffini is aware of that. It starts to fire up the action potential and let your brain know about it. Okay. Do you think this information is useful for your brain? Do you think your Ruffini's corpuscle is very important for your brain? Your brain wants to know about all the displacement of collagens?
Not usually.
Not usually, because if it was important, you would be aware about your clothes right now. You will feel them on you. But luckily, your brain just cancels that information. It says, Ruffini, good job. Thank you for your input. but I couldn't care less. Okay, so I have some other business to run. So it cancels that information. You're not aware. But it's very interesting that in some scenarios, some patients, they are aware of their skin. Okay, they are aware that their t-shirt is on them. I'm not sure how to explain it to you because none of us are aware of it, but they are aware of it. They feel it on their body. So typically you put those patients on antipsychotics, literally very sedative kind of drugs to make sure that they forget everything, including the fact that they're wearing the clothes. Okay, so yeah, that's very interesting. So that's why Ruffini is hair follicle. It's invagination of epidermis. That's the part of the epidermis that is kind of invaginating into the dermis. So that's why we say it is a derivative of the epidermis. Has 4 areas: infundibulum, isthmus, suprabulbar, and bulbar area. You can think about the hair follicle as a bucket or like a pot out of which the hair is growing, right? It's just the pot out of which the hair is growing. So it's very important for the slides because in order to consider a structure, a follicle, you have to see it invaginating. You have to see it do this. So if you do not see it, it's not a follicle, it's a hair. It's not. Okay, so in order to be considered as a hair follicle, full invagination has to be visible. In the bulb area, we can see some additional invagination, which is known as the dermal papilla shock. Okay, so this is also known as the dermal papilla as well. Dermal papilla is a vascularized connective tissue, and it is very important for nutrition because around the dermal papilla, we will have lots and lots of matrix cells. The keratinocytes here, they're called matrix cells. And those matrix cells need nutrients in order to grow. So there's actually a study, like a hair study, that some people have beautiful hair, thick, nice, shiny, okay, amazing hair, because their dermal papillas are very wide. They have lots of blood vessels, so matrix cells have lots of nutrients coming in, so they keep on proliferating, the hair grows amazingly, beautiful hair. And some people have very thin hair, and the answer is because dermal papilla is not as wide. It is there, it's just very, what's the word I'm looking for?
Narrow?
Narrow, like there's a word in Russian language that I cannot translate right now. Wait, like this.
Squashed?
Squashed, yes, very squashed. Okay, so very, very squashed, that you see that it's definitely like too many cells are around it, so it's very squashed that you cannot see the nutrients. They're not trying. They're not diffusing. Okay, so that's, yeah. Okay. Here we have sebaceous glands. Sebaceous glands are always associated with hair follicles. It's very important to know, here the picture kind of does not show it. Sebaceous glands opens up at the level of isthmus specifically, because here for some reason they show like infundibulum, but in our book and lectures they made sure that you know this, the sebaceous glands open up at the level of the isthmus. That's where they drop their sebum. Okay. Now let's do the layers of the hair. So go back to this picture. You can see that hair is inside the hair follicle, dermal papilla, right? So yeah. If your hair is inside the hair follicle, the most outer layer is connective tissue sheath. Okay, so the most outer layer is connective tissue sheath. If your hair is outside of the hair follicle, like here, the most outer is the glassy membrane. So when your hair comes out from the hair follicle, it kind of leaves the connective tissue behind. So it fully exposes your glassy membrane. Okay, so if you're inside, connective tissue sheath is the most outer. If you're outside, this is going to be the glassy membrane. So let's do the layers. What do we have? The most outer connective tissue sheath, then glassy membrane, then outer root sheath, then inner root sheath. Inner root sheath will also have sublayers that we call Handley, Huxley, and then cuticle. Okay, so Handley, Huxley, and then cuticle. Do we see them on the slide? No, it's more of a theory question, but still you need to notice. Beneath the inner root sheath, we have the hair shaft. Okay, so that's the hair. That's where the keratin is present, right? So that's where the keratinocytes are. Hair shaft also has layers. The most outer is again cuticle. As you can see, we have two cuticles near each other. Then we have the cortex, then we have the medulla. Fun fact, almost all men have medulla. All men. In women, only like half of the women have medulla in their hair. So that's why generally men's hair are rougher. They're much stronger. Okay. Again, exceptions like bald people and some additional thing, but like generally females do not have medulla. That's why the hairs are a bit thinner. Okay, a bit thinner, just a bit. I really don't like this topic. It's so boring. Who cares about hairs? So that's the layers. That's the cross section. So here we have the outer layer is the connective tissue sheath. Then we have the glassy membrane. Then this one layer is the outer root sheath. This is the inner root sheath. And this is the hair shaft. Hair shaft has cuticle, cortex, and medulla. You can see that within the cortex, there's this brownish substance. That's hard keratin. That's hard keratin, okay? If they ask you this weird question, what's the difference between soft keratin and hard keratin? Degree of polymerization. That's the answer, degree of polymerization. Basically, in the soft keratin, the way filaggrin works, it makes bridges between keratin intermediate filaments, right? So keratin intermediate filament 1, keratin intermediate filament number 2, and then between it is the filaggrin that sticks it together, right? That's soft keratin. Put 3 to 5 filaggrins between them. That's hard keratin. So degree of polymerization, how many bridges you have between each other, right? So the more bridges you have between each other, the harder you are, the more connections you have. That's for you. That's for you. Sweat glands. We know everything about them. We learned them last semester. That's for you, like as a recap. You know, we have eccrine sweat glands. That's how they look like. They have a very tiny lumen. Their type of secretion is merocrine. They are present everywhere, like your thin, thick skin everywhere. Okay, so yeah. Apocrine sweat glands. Their type of secretion is apocrine, as you know, right? In this university, we say apocrine. In the world, you say merocrine. They already changed it, but in this unit, they haven't changed it. So this is your apocrine sweat glands. House the lumen, very big. And don't forget that they're only limited to like certain places, like your axilla, anus, and whatever. So in our slide, we don't have it. So here's your eccrine sweat gland, and here's your apocrine sweat gland. Nails, I will discuss this on the slide. So here is your nail. This is your nail plate. Nail plate is stratum corneum. So nail itself is the stratum corneum, but keratinocytes here, they have hard keratin. Okay, so they have hard keratin. They don't have soft keratin here. Nail plate is laying on a nail bed. So right under it here, you can see the nail bed. Nail bed is just vascularized connective tissue. Okay, so this is the area which is just vascularized connective tissue. That's it. Here is the root of the nail that goes a bit deeper. Surrounding the root, we have nail matrix. And nail matrix is the place for stratum basale, spinosum, and granulosum. So we have said that your corneum is the nail itself, right? But the nail matrix will have the basale, spinosum, granulosum. They will be proliferating and kind of occupying this area right here. That's the area, the root area. That's the area where they get their keratin. And then the more you add them, the more your nail grows, right? The more it goes outside. If I add more matrix here, right? So the nail will be growing forward. Cuticle, in medical language, eponychium. I don't know why. Under the nail, we have some skin called hyponychium. Apparently, this skin is responsible for keeping your nails straight. Okay, so when they grow straight. They don't start curving, right? So they just grow straight. Hyponychium is thick skin. Eponychium is thin skin without the hair, because you don't have hairs in your cuticles. Distal phalange, cuticle or eponychium, nail plate or stratum corneum, nail bed, vascularized connective tissue. This is your nail root. Nail root is just like the first couple of keratinocytes that are only getting their keratin. This is the nail matrix, right? So this area here, this is the nail matrix that is kind of consisting of stratum basalis, spinosum, and granulosum. And here we have the hyponychium, right? This is the hyponychium, which is the thick skin. I forgot to mention there is like a half moon area called lunula. Lunula just represents the non-keratinized portion. So that's the area where you don't have as much keratin. And in clinical practice, doctors use this area to press on it. Like as a doctor, you press on it to check if you're in a coma or not. That's one of the steps for checking if you're in a coma or not. Ask somebody, like for you, you won't do this as you should. Just press with your nail on your lunula. It hurts, okay? And like the more you press, the more it hurts, especially if you do it suddenly. Just suddenly you dig your own nails into the lunula of another person, it hurts. So if you're in a coma, your reaction is none. But if you're not in a coma, you're just confused or contused, right? Your primitive reflex is to remove your hands because it hurts, okay? So that's what they use the lunula for. Thick skin at the fingertip, right? You can see the stratum lucidum as the bluish line, and this is the stratum corneum. Without even looking at anything, just by looking at stratum corneum, you can say this is a thick skin because stratum corneum is abnormally thick in the thick skin, right? So it is super, super thick in the thick skin. Dermal papillas, reta regis are present here, right? So nothing interesting, exactly the same thing. That's how the dermal papillas should look like, okay? And that's the reta ridge that should look like, the counteracting part. Okay, that's for you when you study. And last slide for today is going to be your scalp, okay? So this area, your skin, three layers, epidermis, dermis, and hypodermis, right? So those are the three layers of your skin. Without looking at epidermis, you can say that this is definitely thin skin. How do you know?
Stratum corneum is very
Stratum corneum is very small.
Without
Very
looking at epidermis, how do you know this is thin skin?
hair follicle.
Hair follicles. Do you see how many? All of those things, those are hair. All of them. Those are your hairs. I don't even want to magnify into this area. I don't need to. I can see those hairs. That's it. This is a thin skin. I can tell you that. So this is a hair follicle. Why? Because I can see how it is invaginating. And that's what we discussed before. In order to be considered as the hair follicle, you have to see the point of invagination. You have to see it. Everything else are hairs. They're not hair follicles. They're considered to be hair because you cannot see the point of invagination. So the same situation, epidermis, papillary layer of dermis, reticular layer of dermis. This is the hair follicle, right? Invaginating. So epidermis is invaginating. This is hair follicle. Right next to the hair follicle are those things called
Sebaceous gland.
sebaceous glands, type of secretion.
Holocrine.
Holocrine.
Right, so those are going to be the holocrine. Okay, what are those? Because they don't look like anything else. Those are the arrector pillae muscles. Okay, so here they are, magnification. Those are the arrector pillae muscles. So they're typically right next to the hair, so they can raise it, right, in case something happens. What about those?
Apocrine gland.
Eccrine sweat glands, because you can see that lumen is very, very tiny, right? So those are the eccrine sweat glands, type of secretion.
Merocrine.
Merocrine.
Merocrine. And here we have the hair. So let's take a look at your hair, a bit more details, because yes, those are the eccrine sweat glands. Here we have some sebaceous, right? So those are the sebaceous erector pilae muscles are here. So okay, here is the hair. What are the layers? Here, the most outer layer is connective tissue sheath. How do I know? Because I can see it's kind of peeling off in a way. Do you see there are lots of separate layers are present there, so it's definitely connective tissue sheath. But then take a look at here. Do you see it's very sharp red, right? Very intact, very reddish, sharp line. So this is actually glassy membrane. So that's how to differentiate. So connective tissue sheath is almost peeling off. The glassy membrane is very intact. So you try from this side. What is the most outer layer?
Connective tissue.
Connective tissue sheath, right? Because you can see that it's kind of peeling off. What about from this?
Glassy membrane.
Glassy membrane, because you can see a very intact red line. Okay, so this is going to be the glassy membrane. So let's do the layers. Here, the most outer is connective tissue sheath, then a little sharp red line. This is going to be the glassy membrane. Okay, this is the glassy membrane. Beneath the glassy membrane, you can see one layer of cells. They stand out. Do you see? They don't stain the same as the rest of the cells. This is the outer roof sheath, or outer root sheath, external root sheath. Why does it sound weird? Is that correct? External root sheath?
Outer, no? Outer and inner.
Outer root sheath. Why am I having outer root sheath? Why does it sound weird? Outer root sheath. Maybe I was saying it too many times, so now it actually sounds weird. Sorry. So yeah, this is the outer root sheath. Okay, yeah, this is the outer root sheath. I don't know. For some reason, when I say outer root sheath, I think of the external enamel. You remember the one in the tooth? Okay, so that's what I'm thinking about for some reason. But okay, so yeah, this is the outer root sheath. This is the inner root sheath. And don't forget, it has Henle-Huxley cuticle, but we cannot see it. So we just say this is the inner root sheath. And then the inner part, this is the hair shaft. On this particular picture, we can't see everything. So for example, this is the cuticle, cortex, and then the center is the medulla, or here, cuticle, cortex, and then the center is the medulla. So those are the areas of the hair shaft. Again, the same thing, hair follicle. How do you call those?
Dermal papilla.
Dermal papilla.
Those?
Epidermal.
Epidermal ridges.
Yes, yes, yes. So those are going to be the retinal ridges or epidermal ridges. This is the papillary layer, right? So this is the papillary layer of the dermis. So dermal papillas, they are the papillary layer of the dermis. The layer at the bottom, this is going to be a reticular layer, right? So this is the reticular layer right here. And you need to remember that a reticular layer has lots of those. What are those red lines?
Collagen type 1.
Perfect. Collagen type 1. So at first they look like muscle. Okay, to some people they look like muscle. Just try to see a bit closer to it without even magnifying. Do you see any nuclei? Do you see any black dots near it? Definitely not. So if it looks so thick and it does not have nuclei, it has to be collagen type 1, the thickest, strongest, baddest collagen there is, and that's it, collagen type 1. Sebaceous glands, erector pilae, right? Hair follicle is invaginating like this. So yeah, the same idea, sebaceous, erector pilae muscles, eccrine sweat glands, the same. Now this picture is important because sometimes they ask this. So this area is called bulb. Okay, so this area of the hair follicle or hair, we call it bulb. And you can see within the bulb, there is something here. What is this?
Dermal papilla.
Dermal papilla. And dermal papilla is a vascularized connective tissue. And you have to remember that it is kind of invaginating, right? So it is just connective tissue, which is invaginating this way. You can see around dermal papilla, there are lots and lots of cells, right? Lots of cells are present here. How do we call those cells? Those are matrix cells. They are keratinocytes, but here we call them matrix cells, just another name for them, okay? And if you pay close attention, you see that some cells are dark. Do you see them? They have like a dark pigment to them, right? So some cells are dark. Those cells are melanocytes. So right next to the matrix cells, you also have melanocytes, and they are responsible for your hair color. Okay, let's do the layers. The most outer layer?
Connective tissue sheath.
Definitely. Do you see beneath it, there's a very strong, sharp red line right beneath it. Right? Glassy membrane, yes, glassy membrane. This? Outer root sheath, and then deep?
Inner root sheath.
Yes, this is your hair shaft, and hair shaft consists of the cuticle, and this is the cortex. So this particular hair, we cannot see medulla. We can only see the cuticle, and we can only see the cortex. We cannot see the medulla. The same is here, right? So this is the hair shaft, cuticle, and cortex. You cannot see the medulla because some hairs do not have it. All of this white space here was occupied by keratinized hair, by like full-on dead hair, right? So keratinized hair. You can actually see a piece of it here. That's the hair here. And maybe you know what I'm talking about. Sometimes, I don't know, you pluck out your eyebrows and you pluck out good, because how do you know, right? At the bottom of that hair, there's a whitish area that has no color. Okay, that's the hair that is definitely still alive. It still has alive cells in it because it doesn't have the keratin. Have you ever experienced this? Like you take out the hair and you see this whitish part at the bottom. Okay, so it's the alive hair. So the keratinized portion is a bit up, right? It's upper. Okay, finally. So next class is the last class. And as I remember, we decided Tuesday, right?
Mhm.
Yes.